Okay, so this is my second time remaking this video simply because the proof is quite hard to explain, but I can't give up without explaining this proof. So, um, let's go over centripetal acceleration. This is just mostly derivation here. We'll show that the acceleration constant. We'll show that the acceleration. I was gonna write something after this, but that's okay. It's on the last slide anyways. Is constant because it makes the velocity change around the circle. So what do I mean? So remember when we went to uniform circle motion or something? I forgot what it was called. But when this is right here and it's moving this way, let's say that no forces act on it when it has already a velocity of this way. That means this is just going to continue going this way until another force says, hey, you must go this way. So let's just say something hits this thing and it starts going this way. And then something hits it and then it starts going this way. And so on and so forth. Simply put, there must be an acceleration that is keeping this thing on track. Okay, so that's the simple logic behind it, but there's even more extrapolation here. So note, I did figure this out. It takes a lot of brain memorization is what I'm trying to say. I mean, not memorization, brain application. So note here that we need an acceleration that is going to keep this thing on the track while maintaining the circular velocity. Now, an issue arises for two reasons. Well, first, we can only denote the magnitude of acceleration. Because let's say the acceleration is, I don't know, I'll just say something small. Let's say 2, and I'm going to start using, no, I'm just kidding, I wasn't going to. Actually, 2 meters divided by second squared. Okay. And let's say it goes in the 90 degree direction. So that means, right here, right? That would be kind of good because then it would change the acceleration 90 degrees to the here. But note that the acceleration is still one-way motion. So it'll keep just accelerating it this way. So what I'm trying to say is that you can only denote the magnitude of the acceleration. Because if you say the direction of the acceleration, it's not constant. And the only thing that remains constant is the acceleration because it keeps it on track. And that's why acceleration is constant. So no matter from here to here, the change in velocity divided by change of time is going to be the same as here to here. So there's a constant acceleration, should I say, and it's acting this entire time. And you can't denote a direction because once you denote a direction, it's going to fly off the circular motion. Great. So now let's get into the proof. And to do so, we're going to use these two image diagrams here. And what got me stuck last time is that I thought this was a velocity vector, which it is. But I thought this was a velocity field, but it's actually a displacement field or distance field or position field with two velocity vectors. So in other words, if we denote this as c and we denote this as the radius, and we denote this as O, and we denote this as P, and this is the radius. This is position. R denotes a radius from the center. But we're having velocity here, so that means it's kind of like a position versus time graph where they put velocity marks in it, but it's not necessarily all about velocity. I'll explain that in a second. So here, let's just say that O is somewhere around the circle. Something is something right here. That means the acceleration is or the velocity is always the tangent line. And I guess that would be acceleration too, but because velocity and acceleration kind of go hand in hand in direction if you use the same vectors. But anyways, that's something different. And we'll say that P is going here because it has to travel downwards, right? So if we took this and just placed down here, we can calculate the change in velocity. And when we do so, we get and these would be the same length, so it would be isosceles. Same length because the velocity is the same. And we will get a resultant vector of delta velocity. And here, we will get theta, A, and B. But note that this is a tangent line, which means that this has to be a right angle. So that means A plus this angle, which let's denote as B actually. Sorry, that was incorrect. That means A plus B must add up to 90. And that means A plus theta must also add up to 90 because this is a right triangle formed here. So guess what? B and theta are the same. And because B and theta are the same and sorry, b equals theta is, should I say, is the right term. That means, oh, sorry, that actually isn't a right triangle. We don't know if it's a right triangle. Sorry, that's incorrect. So that's where I think I messed up. I assumed it was a right triangle. But these are both isosceles triangles. I don't know. I guess it would be V1, V2. So these are both isosceles triangles, and they both share one same angle. Side angle side congruence, similarity. I just figured that out, actually. I thought that was because it was a right triangle, but I just realized that these would be the same length, and therefore it can't necessarily be a right triangle with that as the hypotenuse. So yes, I was incorrect. But now I'm correct. So anyways, now since we established similarity, we can set up ratios. And remember, ratios are always the same between triangles. So for like a 30, 60, 90, if this is 2 and this is 4, then this has to be 1 and 2 because the hypotenuse is always twice the shortest side in a 30, 60, 90. So, since these are the same, we can draw this as a position R, R, and R2. Or sorry, I guess it would be V2. V1, V2 over delta Y. And V2 is the same as V1, so it doesn't really matter. You can say V2 or V1. The only difference is the direction. But we don't care about the direction because we're simply calculating magnitude because acceleration direction is not constant here. It's ever-changing. So that means delta V over V is equal to this side, because it's the same as this side, technically, because these two sides are the isosceles. Anyways, then that would mean R is equal to, sorry, let me think. Sorry, give me 1 second. I just realized it. Oh, sorry. Sorry. Although this is right, this is V2, I forgot to split this triangle up, and that was the issue with my proof. So this would be RR, this would be RR, and then this would be V delta T, and the reason being so is because it's a constant velocity, so there's no summation here, there's no calculus involved. It's equal to V over T divided by radius, simply because they're the same triangle. Divide T on both sides, and then times velocity, and velocity is constant, so it doesn't matter if you use V1 or V2. And divided by R, and as delta T is approaching 0, this thing is becoming more and more like a straight line, so it works. And yeah, that's centripetal acceleration.